Okay, I think we can get started. How's it going, Publius?
It's going, Mod. I think we're gonna try something a little bit differently today, as you and I have discussed. Uh, so, do you want to kick it off, or you want me to kick it off? Uh,
Why don't you? And I would add, I would fill in.
Amazing. So, for context, there was a dev call today for about 2 hours. Publius was presenting the work that they've been doing on pumps, and there was a lot of information presented uh, in a very short period of time. And hopefully, over the next week or so, we will be able to produce some sort of more formal written content to better articulate the trade offs and decisions that need to be made around pumps. But figured it might be constructive to do an hour of Q&A about pumps because we didn't really get to do much of that, and figured it would be smart to start from a very basic perspective, just talking about what the different options are, what the different parameters are, and how things have been architected, and just cover things a little bit differently than they were covered during the initial presentation. So maybe to kick us off, could you talk about you were using all of these terms on the call. Some people may not be as math oriented. So there was EMA, there's GMA, there's SMA. Can you maybe start talking about the different terms and what they mean in the context of a pump?
Yes, happy to. So, kind of what is an oracle used for? An oracle is used to determine the price or, any sort of data point, that exists kind of anywhere in the world, could be on chain or off chain. But kind of what a pump is a pump is an oracle specifically for a well. A well being an implementation of a AMM, most generally going to be used as a constant function AMM. And the idea is that the pump provides some sort of insight into the value at which the well seems to be pricing the assets inside of it. So naturally one would say, okay, you want, and so kind of the question becomes how in what different ways do you want to evaluate the price that a pump is displaying? You take a standard constant product pricing function AMM, where x, y equals k. You can compute the price in the pump by dividing x by y. So if there is a pool with Bean in USDC, there's a million of each token in the pool. You can divide x, the number of beans in the pool, let's say y is the number of USDC in the pool, by each other, a million divided by a million, to get 1. What this means is that this pump, acting as a constant product, AMM, is willing to offer a user to exchange 1 bean for 1 USDC or 1 USDC for 1 bean. It's important to note this is merely just an instantaneous price, and the actual price is a function of, for someone to trade into the pool, the actual price is a function of size. So, kind of if someone, for instance, were to put a million USDC into this pool, I believe they'd only be able to take out something like 500,000 bean, as the price between the assets shifts as the pool, as the ratio of tokens in the pool becomes unbalanced. So how does a how do or at least historically, it's important to take into context historically how different attempts of AMMs have tried to provide some sort of baseline for ways to query the price within a given AMM. Now, one of so of course the most natural way is, what is the price of something right now, or what is the value of something right now in terms of another asset? Beanstalk performs this type of evaluation when someone deposits into the silo. When a user deposits Bean3 curve into the silo, Beanstalk needs to, through some sort of, through some sort of oracle, determine what is the value of Bean3 curve in Bean in order to determine how much stock and seeds to give to the user when they deposit. So, one example of an oracle is an instantaneous oracle. And, one might naturally think, and, let's query the current balances of the pool to get that price. If there's $1 million USDC and $1 million Bean, just query the pool now and say the price is $1. But, in the on-chain world, the fact that, anyone can move some of the balances in the pool has significant ramifications. Most notably, something that happens commonly on chain is a flash loan, where in a single transaction, someone performs some swap in a pool, imbalance, or some oracle manipulation through a flash loan specifically. And what this would mean is someone performs some sort of swap into a pool, perform some sort of action that evaluates the instantaneous price in the pool, and then sells back into the pool atomically, which can be done on chain, as as everyone knows, that transactions in the EVM have to happen synchronously. There's no way for any sort of asynchronous actions to occur, such that someone could perform a sell into the pool after the first buy. Let's say it's a buy that the manipulator does. So this immediately gets you into the territory of, it's not feasible to use the current balance in the pool as an oracle, because it can be very easily manipulated through some sort of atomic manipulation. Now, this then begs to ask the question of, how can some sort of statistical variable be used to estimate a manipulation resistant value of the balances in the pool, which is the used to determine the price? And the first stab at this, as far as we're aware, is in Uniswap v2. And Uniswap v2 implemented an arithmetic kind of sum of the balances of the pool over time, or of the prices of the pool specifically, not the balances. It would compute every time someone swaps in the pool. It would compute the instantaneous price of the previous balances in the pool and add that to the cumulative price counter, both in the x over y direction and in the y over x direction. Now, this proved to be a great implementation of or a great attempt at an initial implementation of an oracle. The Uniswap v2 oracle was used in the original Beanstalk for both minting the BDV of Bean ETH LP tokens, and really just in those two cases. Now, what's there are a couple things that became clear about ways in which future manipulation could occur on this kind of oracle, and that's that and I guess we need to kind of get into the different types of means. So, kind of now considering, kind of the goal is to perform some sort of time historic average of variables in the pool, across, recent history. Let's say over the last, 300 seconds or the last hour, and perform some type of statistic that takes into account the balance of the pool at every single, point, such that for someone to manipulate the entire oracle, there would need to be some sort of manipulation of the balances in the pool at every single time in the past. And now the most, the most, I guess, the most conspicuous way to perform some sort of, aggregation of historical values is through an arithmetic mean, where simply, all of the values are summated and divided by the total number of values. Kind of in Uniswap v3, the use of a geometric mean was actually introduced. And, kind of interestingly, back to when I think it was, Pythagoras was, first, working on his mathematical theories, he came up, he did research into 3 different type of means. The first of which is the arithmetic mean, which is kind of an additive mean, where it's, the sum divided by the number of occurrences. The second of which is a geometric mean. Now, a geometric mean is a multiplicative mean in a sense that instead of adding all the values together, it multiplies them together. And instead of dividing by the number of occurrences, it takes the nth root of the mean. So, kind of in the same way that, kind of, so it's kind of moving, kind of everything into exponential territory, where, if you were to take the log of a geometric mean and perform it, or if you were to take the log of a series and compute the arithmetic mean on the log of the series, it's the same as the geometric mean. So what does this mean in terms of how it actually affects the way that these statistical these statistical formulas, react to variations in the data? Now, for people who are familiar with kind of, some form of log distribution, just go on some, graph log x. And what's really important to note is that, the second derivative is decreasing. And what this means is that the respective, increase, the first derivative, is decreasing. So the delta for variables that are farther away from kind of, that are higher, is lower. And what this means is that when a geometric mean is evaluating values that are kind of outliers, the geometric mean, kind of taking into the fact that, kind of log A, kind of log A plus log B is going to be less than A plus B, kind of implies that, kind of the geometric mean is always going to be smaller than the arithmetic mean. And we're dealing with strictly values greater than or equal to 1 here, as, it should be noted that a property of the geometric mean, given that it's A times B, etc., means that if any of the values are 0, the geometric mean will also be 0. So, I mean, I guess before continuing, kind of gave a bit of potentially a non-structured brain dump there. Curious, Publius, to kind of your thoughts on what has been said so far.
So maybe just to clarify again, EMA, SMA, GMA. Can you just juxtapose the three of them one more time?
Well, we haven't quite gotten to the EMA versus the SMA yet. Really, just evaluating. Have only discussed the geometric mean and the arithmetic mean, and the different ways in which these means react in relation to variation in the underlying series that these statistical formulas are evaluating.
Great. So maybe just then can you then talk about, I guess it seems like now we have a two-axis framework to consider, right? Whether to use an EMA or an SMA, and whether to use a geometric mean or an arithmetic mean. Is that correct?
Yes, this is correct. And just would also say there might be one more axis to consider here in the fact that there are two different ways in which one might be wanting to actually query an oracle or query the result of one of these formulas. The first being the method mentioned earlier, where someone wants the instantaneous value of something, meaning the value right now. The second is someone wants some average value over a period of time. For instance, the sunrise in Beanstalk currently takes the average over the season as opposed to the value right now, and uses the average over the season in the delta B calculation. So there's an additional access in first, what type of oracle are we dealing with? Is this an instantaneous oracle, or is this some sort of cumulative oracle where it's taking the sum at every single interval as opposed to just updating some sort of value? Secondly, what type of mean are we applying to the underlying data? Is it an arithmetic mean? Is it a geometric mean? Or, there is a third type of mean that's frequently used called a harmonic mean, which, is also, so the combination of the arithmetic mean, the geometric mean, and the harmonic mean, kind of cumulatively, the collection of those three are the first three, means, that are referred to as the Pythagorean means, and kind of form the basis of the three ways to kind of measure some sort of central tendency within a given set of data points.
Okay, so there are now three axes. So far, you've talked about arithmetic means and geometric means. Do you want to talk a little bit about harmonic means and why you haven't discussed them thus far, or you don't think that would be helpful?
Yeah, I mean, unfortunately, am not too in the weeds on harmonic mean. Um, you know, um, it is, my understanding that, kind of harmonic means are more used when dealing with rates, but quite frankly, not too familiar with harmonic means, and am not aware of kind of the arithmetic mean kind of naturally is the most natural mean to consider. Um, the geometric mean is quite present in kind of financial, kind of in common financial applications, um, in the fact that the arithmetic mean is not great, kind of is better for distributions in which there is an independent set of data points, which, arguably a time series is not. And, kind of thus, there tends to be, a use case for the geometric mean, and when it comes to kind of time series problems. But yeah, not too familiar with the harmonic mean. But it is worth mentioning, and perhaps some research is warranted into its use case.
And if to return to the cumulative versus instantaneous axis, if the only thing that needs to be queried is the instantaneous value, is there still the requirement for a pump? And if so, do the requirements of the pump change depending on whether the value that is being supported is cumulative or instantaneous?
So, yeah, I mean, if if you're saying if there is no need for an average over time, is the only do you only need the instantaneous mean? Was that the question?
Well, I guess the question is, do you have to specify in advance whether or not you need the instantaneous or the cumulative of one of the means?
Well, this is ultimately depends on the actual implementation. And kind of there are numerous kind of efficiency and optimization considerations, to be made about how you want to, kind of specify which oracle you're using. But any of them could be implemented in any fashion. And, only when restricting ourselves to the realm of, reasonably, reasonably costly computation in the EVM, do there start to be limitations imposed around how and when, how to implement the different types of oracles, and what that means insofar as when you have to call them, and how kind of do you need to specify them. This is most notably the case for the SMA. Happy to go into that a little bit more.
Sure. So before you do that, could you talk about an EMA versus an SMA?
An SMA is a or what kind of, given that it is always desired to evaluate something in the current time. There is a need to use a moving average. As time progresses, these statistical variables, which are averages, need to kind of move alongside the present. And there are two main types of moving averages. The first of which,
meaning just sorry to cut you off, meaning the arithmetic mean or the geometric mean, those values need to be changing over time. And so the question is around how those values change over time.
exactly.
So in this case, these would only apply to the cumulative oracle and not the instantaneous oracle.
It applies to both of them, as both the instantaneous and the cumulative oracle perform some type of aggregation of data points, and whether to aggregate the data points arithmetically, meaning the summation divided by the sum, versus geometrically, meaning the multiplying together and raising them to some power between 0 and 1, or some negative power, is kind of the question.
Sure, but that applies to both instantaneous and cumulative oracles. But what
Yeah.
about with regards to the EMA and the SMA? Is that only applying to cumulative oracles in this case?
So, I mean, arguably both the SMA and the EMA, can be used as cumulative oracles. As
But
kind of
not instantaneous oracles?
they both could be used for instantaneous oracles too.
So so that it's really 2 by 2 by 3, the whole system. So there are like 12 options.
Yes,
Great. So could you maybe talk about EMA versus SMA?
happy to. So getting back to into a moving average where, kind of we're existing in this time t, and the goal is to use the past, n values and perform some type of aggregation or averaging of the values to determine some measure of central tendency in order to prevent any short-term manipulation or outliers from impacting the value of the query in a substantial fashion, while also ensuring that the oracle is tracking the current price to the best of its ability. It's a real fuzzy ground, as kind of the best price is the price now, the instantaneous price. But the price now, the price in this block at this time, is manipulatable. And, the price at the end of last block is also manipulatable. The price between any two blocks is manipulatable. So therefore, there becomes this notion of now, because instantaneously all of these, blocks might be manipulatable, how do we create some sort of estimation of the price now using historical values, using some historical aggregator to get rid of the outliers? Now, the SMA and the EMA both use some aggregation of, the past n values. The difference is in how much they weight each of the individual values. In the SMA, all of the past n values are all weighted with 1 over n. The SMA, kind of is, kind of very similar to, the SMA just, kind of weights them all the same, and thus, the SMA really is just, a basic arithmetic or geometric mean, where you are summating or multiplying together all of the values and then, reducing it based on the total number of occurrences. The EMA is slightly different in a sense that its algorithm is given some alpha A, and depending on how you define it, it can be, a small value or a big value, but it's between 0 and 1. Now, the average in time t, the EMA in time t, is equal to the EMA in t minus 1 times 1 minus alpha plus the new value times alpha. And again, it might be written differently such that alpha is on the past term, or alpha can be on the present term. But in general, there's some notion of, take the last value, multiply that by 1 minus alpha. Alpha is likely to be small, so 1 minus alpha is going to be about, close to 1, plus alpha times the current value, which is going to be, incredibly small. But kind of what it's doing is averaging together the previous value with the current value based on some weight. So what this means is, instead of the value being some, weighted average of 1 over n of all historical values, the EMA weights the value now as alpha the value last value as alpha squared, the value before that as, alpha cubed, and etc. Or I guess it would be alpha times 1 minus alpha. My bad. So value now is alpha. The value last block is, alpha times 1 minus alpha, which is some number that's just slightly smaller than alpha, because 1 minus alpha is very close to 1, and alpha is incredibly small. So alpha times 1 minus alpha is going to be just less than alpha. And the value 2 timestamps ago is going to be weighted with alpha minus 1 squared, which when you square a number that's very close, that's less than 1 but very close to 1, it's going to result in a number less than 1 that kind of is, slightly more less than 1, right? Like you take 0.99 and you multiply that by, 0.99, or I guess you take, I don't want to do that in my head, but, you get the point. So kind of the notion here is, instead of all of the past n historical values being weighted as, as 1 over n, the EMA takes in every value that's historical and weights it by alpha times 1 minus alpha, kind of 2 to the n, and therefore there's there's some rate of decay on the weight of each point.
So this is very constructive. So there's 3 axes on which to consider the design of an oracle. It seems like the cost of adding any particular iteration of the 12 that we've discussed along these axes would add additional gas costs. Is that correct?
Yes, and the gas cost for each of them varies dramatically.
And so can you talk a little bit about the implementation of pumps that you've developed thus far, which of these 12 iterations it supports, and how composable the different iterations are, and what needs to be chosen when?
Sure. Yeah, I mean, maybe even it's helpful to start with, kind of the relative gas cost of each of these different 12 variations. So first off, between the geometric mean and the arithmetic mean. The geometric mean requires performing some kind of complex, high precision exponentiation that's quite difficult on chain, or it can convert everything into log terms and perform, kind of contain the logic of an arithmetic mean. And the latter is, currently what is implemented, and
Contain the logic of an arithmetic mean or a geometric mean?
it would, if you take the log of everything and apply an arithmetic mean and then, exponentiate it back out, it's the same as an arithmetic mean.
The same as an arithmetic mean, not a geometric mean.
Is the same as a geometric, yes. Apologies. If you log everything and take an arithmetic mean, that is the same as a geometric mean.
So you're saying that there is a gas efficient way to implement it, but there's some loss in precision?
I'm saying there is a way to implement it, but kind of complex, mathematically complex operations are expensive on chain, and logging and power are actually not very cheap, especially when dealing in floating point terms. So kind of the log operation itself has a gas cost, I think, of like 7,000 gas or 5,000 gas. So the exponentiation can probably be, a couple thousand. So let's say that there's like a fixed overhead of like, let's say 10,000 gas per value for using a geometric mean over an arithmetic mean. And, it should be noted that if, if a geometric mean is already being used, storing a second oracle that also uses a geometric mean doesn't require imposing that gas cost of logging and exponentiating in and out is not necessary. So now the next is, first off, when it comes to a cumulative oracle, using an
Is
EMA.
that different? Sorry, just to interrupt. Is that different for an arithmetic mean? Meaning, you're saying that a geometric mean?
So the geometric mean equals the arithmetic mean plus one log operation and on write and one exponentiation operation on read.
But if you're doing multiple arithmetic or geometric means, the gas cost does not increase.
Yes. So, for instance, the current implementation of the pump, uses an SMA as a cumulative oracle and an EMA as an instantaneous oracle. The log, they both use geometric means, and the log operation.
Hold on. Let's just before we talk about the current implementation, let's just get back to.
Yes, but my point is that there are two different oracles here: an instantaneous oracle and a cumulative oracle, both using a geometric mean. Because they, are both using a geometric mean and are contained within the same block of execution, the log on write only needs to be computed once.
And does this scale to multiple times? So you can take the geometric mean across multiple different times, or you have to define the time in advance?
So this gets into kind of the EMA versus SMA and, how its on-chain gas costs, kind of tie into this whole thing. So for the SMA, there are two use cases for an SMA as stated. It could be a cumulative or it could be, some instantaneous. Uniswap v2 uses a cumulative arithmetic SMA. Uniswap v3 implements an instantaneous geometric SMA. And that also serves as a cumulative geometric SMA. Now, it's important to note that if it's intended to use the SMA as an instantaneous oracle and a cumulative oracle, it's significantly more, and inherently in having an instantaneous SMA, there's a way to, determine the cumulative over time through its implementation, which kind of we'll get into now. So if using just a cumulative SMA, it's required to, only update some running sum. And kind of in order to calculate some SMA on chain, the way it's normally done is by taking the current cumulative of some statistical variable minus the cumulative statistical variable 30 blocks ago, subtracting the difference between them and dividing by n. And I guess to get into why you even have to do that is, so what is the SMA? It's some addition of the balances over the last 30 blocks. Let's say the balance was updated in every single one of those 30 blocks. In order to kind of summate each individual occurrence, when you read from this SMA, it's now saying, read what, you have some array, which is like the balance at every single block, and it's saying read the last 30, add them together and divide by n, right? Like that would be some, simple implementation of some SMA. Now, on-chain storage, storing one occurrence is expensive. It costs 20,000 gas to store a single value. Now, what this means is that, kind of the cost of every time someone performs a swap would increase by, 20,000 or, per value, or maybe, it depends on how you group them. There's some gas optimized ways to store multiple variables in a single slot. But, generally it's around 20,000 per balance. And that's relatively expensive. On read, you now have to read every single one of these variables. And let's say there's 30 different variables. The cost of reading is, a bit over 2,000 gas. So reading 30 variables is, like 65,000 gas about, which is incredibly expensive. So instead of using this format where you save every value and then read the past n and add it together, a basic cumulative SMA arithmetic oracle, and again, the relative difference between arithmetic and geometric is minimal here, only the additional cost of that log operation. But kind of instead of storing each individual occurrence, it stores the summation of x over time. So it stores x at time equals 0 plus x at time equals 1 plus x at time equals 2 plus x at time equals 3, etc., etc. So if you snapshot that, let's say at time n minus 30, and in time n, you want to determine the SMA over the last 30 blocks, if you have saved the cumulative at time n minus 30, and you know the value now, you subtract the sum at time n. You subtract the time at you subtract the cumulative at time n minus 30 from the cumulative at time n. You get the value at time n minus 29 plus n minus 28 plus n minus 27 plus etc., etc. So the point is, you can, through the use of some cumulative, by snapshotting it at some point and evaluating it now, you can, with only reading kind of 2 data points, determine the sum of all of them. Now, what's important to realize, so this gives you kind of one storage variable that just needs to be updated on each execution. So you get an update instead of a create, which is 5 times cheaper. Actually more than that, because a create also costs to read. So a create is around 22,000. So you get, instead of a create, you get an update. And instead of having n read operations, you only have 2 read operations. And, that's essentially what led to the creation of that is how Uniswap v2's Oracle worked, how Curve's Oracle works currently, and the Oracle that pretty much Beanstalk uses. Now, Uniswap v3 took this a step further and wanted to create an instantaneous Oracle. The difference from a functionality perspective between a cumulative and an instantaneous Oracle is that with the cumulative Oracle, you're required to snapshot some start. And with the instantaneous Oracle, you don't need to snapshot the start. In this implementation of it, so what Uniswap v3 did is they basically said, we're willing to impose that cost of 20K per swap to allow people to say, okay, to get rid of the requirement to snapshot the start time. When Beanstalk was initially deployed, it didn't use a flash loan resistant Oracle for anything. And when it was first realized that a flash loan resistant Oracle was necessary, it required implementing some sort of BDV Oracle for the Uniswap v2 LP token price. And Uniswap v2 uses this cumulative method, right? Where it's like some snapshot, and then over the snapshot, you take the average. Now, it was extremely difficult to try to create an oracle that inherently is instantaneous in nature, meaning when you deposit, you need to know the BDV now. And what this means is that there's no fixed, is that you're not able to snapshot the start for every single timestamp, where in any single block, someone could deposit, and in order to determine, say, the 1 hour SMA using Uniswap v2, it would need to know the start timestamp an hour ago, which means that, it's inherently required to know the start timestamp at every single, or what the cumulative was at every single time. And so, ultimately, the implementation, and you compare that to something like the Sunrise knows it's not going to need to read the cumulative until the start of the next season. And at the start of the next season, it can just use the snapshot that happened during the Sunrise call prior, take the average over that time period. Because there's fixed control of execution at both the start and end of every time frame, it can use the snapshot method. But when it comes to something, because it knows it happens on some fixed schedule, and in reality, Beanstalk is quite unique in the fact that it even has this type of oracle to begin with. There are a few other protocols that are operating on some, fixed time frame, and thus very quickly, kind of for any protocol to use Uniswap v2, it becomes almost an impossible task. The solution that Beanstalk ultimately ended up using was it would take the average so far into the season, and if you tried to deposit Uniswap LP tokens in the same block after a Sunrise, it would actually fail. And this was quite a mess, as it would either be incredibly expensive from a gas perspective to start, to remember the last one. It would change another cost of updating to a cost of a create or 2 updates. So therefore, kind of, there was no fixed look back on the oracle. It was basically, how long has it been since the Sunrise? Take the average over that. And so one can see how very quickly the cumulative oracle, is not that useful. And so Uniswap v3, pick the kind of solution in between the first one, where you count all of the individual values, sum them, and divide by n. It used, instead of storing the value at every single x, it stores the cumulative at every single x. So kind of reading or writing it, increases the gas cost by about 17K, but on reading, it can only increase the gas cost by log n, kind of by log n, which is when n is sufficiently small, probably less than 10,000 gas. So kind of it's able to make serious increases in efficiency over the cumulative oracle, but the SMA is still incredibly expensive when used as an instantaneous oracle. The EMA only, similar to the cumulative, each iteration of the EMA, each time the EMA steps forward, it only requires one on-chain update, very similar to the original cumulative, because it just requires, adding, kind of, because this version equals the last version times some variable plus the current version times some variable. It doesn't need to know anything about the historical, observations at all. However, to use it, as a variable cumulative, in a sense that there's also some notion of, how far can you look back? And is the look back fixed? The main trade-off between, one other trade-off between an EMA and an SMA is that in an SMA, you have a variable look back. In this Uniswap in the Uniswap v2 implementation, you can choose to snapshot at whatever start time you want. In the v3 implementation, you can you can always look back further, as you have a list of the cumulative every time it's changed, up to some max variable, where max is, reasonably high, maybe a day, like a look back such that no one would want to look back past, just to impose some restrictions on the upper bounds of computation time. But kind of the point is that there is a variable look back, such that if Beanstalk is using, say, a 1 hour look SMA for the BDV to determine the BDV of a token, then and wants to change that to, say, 30 minutes instead of an hour, then it just has to change the parameter it calls the SMA with. But again, it's an expensive call and it's an expensive write. With the EMA, alpha is the variable which ultimately controls how far the lookback is. If alpha is, say, 0.5, the mean is weighted 50% by the newest value. If alpha is 0.1, the newest value is only 10% of the mean. And so by having a smaller alpha, the look back is greater, but it's required to know alpha ahead of time. And if an oracle gets deployed targeting a 1 hour EMA, then, and the Beanstalk DAO wants to change it from an hour to 30 minutes, it would require deploying a new liquidity pool, and somehow they'd have to tweak incentives to get LPers to migrate into the new liquidity pool, which uses the new pump. And, it's a lot messier, so kind of, an important note is that the EMA oracle has a fixed look back, and, the SMA oracle, whether used for cumulative or instantaneous queries, has a variable look back.
Sorry, didn't realize I was muted. All right. So maybe, and we're running out of time here, but maybe just to frame the things that people should be thinking about heading into this week of discussion, can you talk about the current pump implementation and what types it supports?
Yes. So the current pump stores a Uniswap v2 kind of style SMA, but it uses a geometric mean. The geometric mean was chosen based on how geometric mean reacts to outliers. As stated earlier, because operating in log space, when increasing or it takes in outliers into account less than the arithmetic mean. But an important consideration is it behaves very extremely around 0. So there probably will need to be some limitations set to be, so the minimum oracle value, which personally feels like has very small effect in practice, as it's likely that the wells will maybe lock some liquidity to start, similar to how Uniswap pools do, so that dealing in such stream situations never happens. But basically, so there's a geometric cumulative sum that's intended to be used for the season call, where every season, Beanstalk will snapshot the total and then take the delta over the range and then use a EMA for instantaneous value queries, with some, that does have the implications of a fixed look back, but and so there'll need to be a decision made by the Beanstalk DAO on, kind of what is the look back that is anticipated to be approved for whitelist in the case that it is. But it provides gas efficient writes and reads for instantaneous value queries as opposed to the SMA variation. It's also important to note that none of the types of oracles discussed today natively have any protection against multi-block MEV, and there is a variable capping the percent increase across a block to some fixed percentage in order to minimize how the magnitude of outliers created by manipulators on the oracle.
So there's other parameters in addition to these axes for oracle design that need to be considered. So maybe just to try to understand the pumps that have been built so far. You said there's a geometric cumulative sum. Is that that means that
SMA.
It's an SMA for a geometric sum to be used over time, and that has a variable look back. So that can be used for minting over, in theory, any period of time.
Yes, but it requires control over the execution, of execution at the desired start look back to snapshot the cumulatives.
Great. And then this oracle, the pump also has an EMA that supports instantaneous value queries as an arithmetic or a geometric mean.
Also as a geometric. As noted, kind of the increased gas costs for having multiple geometric means in the same block of logic, helps reduce the gas cost of storing multiple geometric means.
So the pump has support for two different geometric means that are being calculated. One is a cumulative SMA, and one is an instantaneous EMA.
Yes.
And go ahead.
Go ahead. Yeah, I mean, it also stores the capped balances of the pool so that it can determine what the new cap is. So it should be noted, kind of the cost of, capping the value as it changes per block is relatively expensive. Probably looking at something like, 5,000 to 7,000 gas per iteration. But multi-block MEV attacks are quite, are very, are a threat to oracles, and it's important that they're resistant of it. So kind of each oracle is required to store the last capped balance in order to kind of determine what the maximum increase and decrease that should be tolerated is.
All right. Well, we've gone for an hour. Feel like we could definitely go for at least another hour, but we'll keep it to the hour limit that class is booked for. Maybe we run it back for next class, or even book a bonus class in the next couple days. But thank you very much, sir.
Thank you. Hope the majority of what has been said is coherent. Apologies for not being able to, always say things in a concise, efficient manner.
Felt like you did a fabulous job here, sir. Don't be sorry, sir. Thank you very much. Take care, everyone.